All right, so let's start on time. I know some people are probably still eating, but let's keep the schedule on track. So, welcome to the Scalding talk. And a few words about me. I'm a hacker at TypeSafe, which means I'm on the akka team. So why the hell is a akka team member talking about Scalding? Well, okay, too much feedback. Yeah, that's because for the last year I've been working a lot with this thing. And that was before I even joined TypeSafe, and I still think it's interesting to share my experiences. And if you have used Scalding or are planning to use Scalding, I think that's very useful and a kind of experience report. Yeah, so that's me. And random question to get this thing started. So do you know how old Hadoop is? I know it's a tricky question, but I have Scalding stickers, so it's worth answering. Almost. In between. That depends how you define it. Let's define it maybe by the publication of the MapReduce paper. That's actually 10 years now, so as old as Scala. So it's funny to see these two separate thingies converge after 10 years. And yeah, the Hadoop itself, if you define it this way, then it's more or less 2005. So that was the Yahoo implementation, from which now the Java implementation that we all have available from Apache stems. So, and yeah, one other question. Who has actually used Hadoop? Hands up, please. Okay, who is maybe planning or will have to work with Hadoop? Okay, so you're in the right thing, I think. So, what is the actual landscape? Oh, maybe one question. Do I need to introduce Hadoop, what it's doing at all? It's counting words. That's what it does. Okay, so Hadoop. Hadoop is this guy, and the talk is about this guy. So whereas the yellow elephant is happy, the red elephant is angry. And this comes from this frustration of dealing with the yellow elephant. But you'll see why. But it's actually not a very descriptive, realistic, kind of holistic view on the picture, because Scalding is a DSL for Hadoop for the MapReduce pipeline, that's true, but it's using Cascading as an intermediate layer. So most of the abstraction we will be talking about are actually coming from Cascading. So fields like word, fields, and pipelines, etc. That's all Cascading terminology, and it does leak through to Scalding. We don't really try to hide it, because we need to understand the underlying abstraction anyway. But there can always be another layer. So nowadays, the Twitter guys have developed what they call Hummingbird. And Hummingbird is another layer, because you can solve any problem by adding another layer of abstraction. And Hummingbird is aimed at running the same job, whereas some data transformation thing that you describe in your Scala DSL. But then you can pick and choose if you want to run it on the thing on next to Scalding is Storm, Twitter Storm. So it's still in the Apache incubator, and it's very much comparable to Spark. Have any of you been in the Spark talk today? Right. So this talk is not at all about Spark. Sorry. But how does it compare? So it's very similar in the sense of it's for large amounts of data and transformation and preparing this description of the data transformation. And then you submit it, and it's doing the thing. So there it is similar. But in other things, not so much. And Spark is actually powered by Akka. And Scala, you heard it, right? So, also, there's a possibility that Cascading will be able to run on Spark instead of run on Hadoop infrastructure. So this would mean, and that's only a few emails on the mailing list now, so don't take this for granted, but in theory that would mean that our Scalding jobs would be runnable on Spark, so without changing our implementations. But since we don't have people here, at least I don't think we have, that have existing Scalding infrastructure, that's less of a concern for you guys. But if you have 100 jobs already done in Scalding, that's a very tempting thing. So you can abandon the MapReduce pipeline and move over to Spark, which is, as we heard today, faster. It really is. Yes, and then there are Akka streams, which have a very similar API to what we'll be showing here today, and it's completely unrelated again, but I wanted to bring it out explicitly that we are aware of all these projects, and they all fit a different niche. So Spark is this more real-time focused thing, Hadoop is the batch thing, and Akka streams, the focus on Akka streams is the back pressure part. So none of the other projects are actually dealing explicitly with back pressure. I mean, it's a batch job, it's reading a file, right? It's not too much back pressure you need to do there. So this talk is about these guys. So why do we actually need Hadoop and all this very big infrastructure for transforming data? I mean, I can do the same with just Scala. Well, obviously, the problem is that it doesn't fit in memory. That's the only reason we need all this very big infrastructure and many servers computing this thing. Yeah, a quick reminder, if you haven't seen the Hadoop APIs, which is basically what we'll be trying to run away from, but still use underneath, this is how a word count app looks. So that's only counting words. So that's a lot of lines. And the abstractions are very non-intuitive, if you ask me, because there's you have to extend a MapReducer base that extends a reducer, and then the fields there, so the text intritable mean what kind of tuple comes in and what kind of tuple comes out. And you have to put this explicitly in the type there. So a few years later, we can do better than that, but the architecture itself is pretty smart, and we can still use it for many things, because it's very good for parallelizing this map step. Reduce cannot always be parallel. Well, to some degree it can, but the big gain is just slapping a bunch of servers onto your computation and leverage this. So the classical example, the word count, you have some words. When you split them, then you do this funny trick of assigning a number to a word. What we do here is we take each word and give it a 1. And then in the reduce phase, you basically just sum them together, right? So this makes sense because Hadoop's infrastructure, it's easy to write like that. You can produce these tuples very nicely, and then the reduce step is the summing. Although it's not the most intuitive way, I think, of writing that thing. And at the end of the day, you get your works and the accounts. So let's look at the Scalding API finally. So the idea of Scalding is to look like Scala collections with some tweaks. So whereas this is our good old map, the Scalding API, what you should notice here is these guys. So you don't just map over a thing, but you map a specific field from that file. Okay, so you're reading a file or reading a source, and let's say it's a CSV. So each column would have some name. So these are the names we use for picking out stuff. The reason this is good is if you have a very big, a lot of very long tuple, like 20 elements, and you only operate on 1 or 2 fields, you don't have to read into memory all the fields, right? And there are specialized data formats that store this in a columnar fashion, right? Like HBase does, and the today mentioned Parquet format. So you don't have to read into memory the fields that you don't use. This is how it is solved in Scalding's field API. And yes, you have to explicitly say the type here, which is again different than plain Scala collections. The reason is that, well, Hadoop operates on text files. So you need to basically select some type that Scalding will deserialize into. And you can provide your own deserializers, right? So this could be map over person if you provide a tuple converter from tuple something to person. And we'll see examples of that later. And whereas the number is what we read in, the doubled is what we produce into the pipe, basically. So both fields are now available in that pipeline. Okay. So there's another difference of What if I just transform this data and I basically want to discard the intermediate values because it has been a few steps and I want to discard the data? Well, in Java land, that would be nulling a field. And in Scalding, you just operate on map to instead of map. So in this case, that's actually wrong. This would be number 2 doubled, sorry. And the doubled stays in the pipe, but the number is removed. Right? Imagine this number. Obviously, this flat map looks the same way as you would expect. So we're good here. And of course, since in the callback here, we can do anything a normal Scala program can do. So we can choose to iterate outside. So after the flat map step, do another map step, or right away inside the flat map step, do something. So you can move the map inside. Does the same thing by the end of the day. Okay, and the group by, which is well, arguably the most interesting operation for our kinds of jobs, because we need to aggregate things, right? That's what you do with the big data systems. You have too much stuff. When you try to filter it a little bit, tweak it, and then you aggregate things because you can't possibly understand a few terabytes of stuff. You need maybe top 10 shops in my city or that kind of things, right? Okay, so here you group by some field name, right? Works as expected. And what is maybe unexpected is in the callback, here we get, for each group, it will be a group here. So inside we get, okay, so we're grouping less by 10. So it will be less by 10 and greater, right? 2 groups. And each size will be 2. And there's more operators here than just size, like average, mean, and whatever you would expect, right? And you can, of course, fold on it. And if you can fold on it, you can do a lot with it, right? Whatever data structure you want to build up, that's a good place. And then it becomes available in the pipe again. In this case, implicitly named. So the size will emit a less than 10 count field. So that's implicitly, but you can say it explicitly. Okay. Group by. So that's an example and of using another group operator, summing, very easy. And here we name it explicitly, right? So we use the symbol to name the target field name, right? So it becomes available not as less than 10 sum, but total. And how do you actually run a Scalding job? That's it. You just need the tool runner. Notice that the tool runner is the plain Hadoop thing. And then Scalding has its own tool, which is basically like a main that will take care of distributing the jar. Well, not distributing the jar, scheduling the jobs. Okay. So let's see the word count example. That's the canonical thing, and then we'll move on to more interesting things. So you just have to extend the job, and args are this Scalding provided helper method for doing argument parsing. So what you do here is you say, I need an argument input, and what this will do is it will not run the job until you do minus minus input something. So it is a requirement, if you want to see it as the known from Scala and conventions. Okay, so we have a text line that's some input file. So a text line means we will be iterating over this file line by line. And again, implicitly, it has a field name of line, which is why here I can use the, I will be reading the line thing. Okay. Then we flat map into words, just splitting by space or something more convoluted if you want to. Then we group by the word, and we simply just get the size of that group, right? So we don't have to do this weird emit egg 1, and do the sum. Although that's the classical way. This is more, I think, in these terms and not in terms of, yeah, how would Hadoop do it? Yep. Shorthand works here because the type is known, unlike on flatmap, where I said you have to specify the type explicitly. And then you just write it. Here TSV means, and it's rather popular if you use it for testing stuff like writing. Before you submit your big job, you're testing it locally, you want to see if it makes sense, less or not, more or less. So TSV is nice because it's tab separated instead of comma separated, which gets very messy sometimes. And yeah, the biggest feature is that it's actually 4 lines versus a few hundred in the plain Java APIs case. Okay, that's all nice and fun, but let's spend the day in a, yeah, some people call them data scientists, but we are not a very smart data scientist. We'll be doing rather simple things here, just to show the APIs. So, when you read an TSV, you're also able to, because you know you have so many columns in your TSV, so you name them explicitly here in the first line, right? So this is a mapping you have to do explicitly. Can't be really done magically, although, yeah, good question. Actually, it could be, but it isn't. Live. Okay, then we group by the shop ID, and we try to answer the question of how much are my shops selling in total. I have some shops, and in total, number of items, how much do they sell? So we group by the shop ID, and then we take the sum of the quantities and emit into the total sold items field. Then we simply write this. So that's the output. And notice the output does not contain the other things, right? Because in the input, we had 4 fields. But after the group by, which translates to a MapReduce reduce phase, right? So we only have whatever we were emitting here, plus the join key, which in our case is the shop IDs and some numbers of sold items. Yeah, let's increase the readability of these examples by writing the header, which helps a little bit, at least for examples. And then let's try to improve this query, because that's still not very useful. It's still quite a lot of shops. I have a lot of shops, and I want to find the best-selling one, right? Or worst-selling one. I'm not interested in just the counts. So, how do I do a sort on a big collection of things? So we do a group all, which is a bit counterintuitive. So group all means I need these grouping operators, but over the entire pipe. That's why group all. There isn't a group key to group by, just everyone with everyone. And then we can sort by, and as this is not directly executed, right? Same with Akka streams and Spark and everything else which operates this way, you just prepare this graph of operations. So when I do sort by, that doesn't mean I do something. I just signal the intent I will be sorting things to this graph. So the reverse means, yeah, descending order, right? Okay, so now we know shop 2 is the top selling shop. In terms of item count, at least. Not money made, but that's good enough for us. So, how would I take the top 3 shops? Well, in theory, you could just do the previous job, then download the output file, and yeah, head the 3 elements from that file, right? First 3 lines. But why would you spend all the time computing all this data if you don't need the entire data? So, in theory, this is what you can do. In practice, you wouldn't, because it's very inefficient. Why? Because what we instruct Scalding to do here is do the sort, do the take. And sadly, the optimizer isn't smart enough to see, oh, the guy just needs 3 elements. So I could optimize that, and yeah, let's go into it right away. So what you can do is, you have your map step, so 10 mappers doing something, And then the data is being transferred from one set of nodes, the mapper nodes, to the reducer nodes, right? It has to go over the wire. So the problem there is, why am I sending over all the data to then just take 3 elements in the reduce steps? What you can do is, if the mapper, each mapper would only send his top 3 elements, then it does converge, right? Because the worst thing that can happen is one guy has all the top things, and the other guys, send each 3 elements that will not be used, right? That's the worst case. The not worst case is this guy has the top guy, this guy has the not top guy, but in the reducers, we can easily filter that out, and we send a lot less data around the network. And this is a big problem. I mean, we are talking about giga or terabytes, it depends on your company, right? So decreasing the number of sent around data is a good thing, and this is a slow thing. So what can we do instead? We can do a sorted reverse take. So this guy is signaling the intent, sort, but I will be taking only 3 in this case, right? And again, we use the total sort and total sort, and I emit to an X. It doesn't really matter how I call it now. Although, there is a problem with that. This is what would end up in the CSV, in the TSV. Yeah, it's a Scala list. That's not what I want in my list. I want to have 3 rows with 5 and 100 something and etc., right? So what? So the problem is, sorted reverse take is, as I said, efficient. It can do what I explained a little bit before, that we don't send the data around too much, but because it does it on the map side, it does it on lists. And this is what you get, because then it merges the lists. And sadly, it's not sophisticated enough to do the right thing right away. So we have to do a small trick with, this line actually. So we take the X, which was the list, and we flat map basically using an identity function, which in a flat map actually does change the structure, right? And this will produce the output that we actually wanted. So it's this small little catches that you spend some of your time on during developing Hadoop things, and specifically cascading things, because sometimes you don't know what type you're sending around. And as you can see, the API is not typed. You're guessing the types all the time. So that's a downside of cascading. And we'll get to the typed API, which can help at least see this blowing up during compile time, and not after 12 hours of computing the thing, and then I have wrong data in my files. That's the worst thing about Hadoop, is the latency of your initial response. Maybe you did a very small error, but it, completely broke the data. Okay. First the job, happy me. So how does all this actually work? So there's going to be a little bit of maths, not too much. And I won't say the other M word, so don't panic. But we'll focus on monoids, because that's the one abstraction that gives most power to all these mechanisms, where we just spread out the work and then merge, merge, merge. So a monoid is defined as some 0 element and a plus operation, sometimes called just op. And 3 laws, because the interface doesn't say everything about it. So the first law is closure, which we define as for every A and B of some type T, the output has to be in the same type. Well, in Scala that's easy, because the type system does that for us in the signature of the plus method, right? I can only add T's, output is a T. Well, or subclass, but we don't care about that. So the other one is associativity, which gains us the parallelism, right? Because if I can first add B and A, or first add B and C, and just keep merging them, that enables me to do A and B in parallel somewhere, right? And then we keep just merging them. So that's the enabling factor. And the other one is concerning the zero, because every mapper, every anyone who will be executing stuff on a modoid, to not be Hadoop specific, will basically do a fold using the zero element, and then add elements to it, right? So it's like a fold left, fold right in Scala. Why we need that is because the point at which you split your data set, you have 10 elements, and you can split them in many different ways. And if this last law wouldn't hold, you could accidentally corrupt your data because, oh yeah, this one element can't be added to 0 because it breaks. So we need all these three. What does this gain us in real life? As you can probably guess, it gains us the ability to execute things on the map side. So we start the reduce phase. Well, we do a map side reduce, basically. By map side, I mean still on the mapping nodes, before we send the data over to the other node, which does the proper reduce step with all the data sorted by key. So this allows us to send a BA2 instead of BA1, and someone does the merging. So already this is decreasing the number of sent data over the network. And there's many things you can do with monoids, so it's not only sum. I mean, I like to call that method plus, and in most libraries it is called plus, or a written plus, as in word, not symbol. But you can do these kinds of operations also on averages. We just saw the sort with take. It operates on the same principle, and other things. Thank goodness you don't have to implement all these monoids yourself, but there's a library also by the Twitter guys, Algebird, which is basically an abstract algebra library. So they provide some very nice collections, approximate collections, because sometimes you don't need the entire data. You just need a Bloom filter, for example. A Bloom filter is an approximate data structure. This will, you create one, and then you create this set. So what a Bloom filter does is it doesn't keep all the elements, and the semantics it provides are similar to a set. The one point where it's different is that it has some certainty. So you give it data, it stores it in, it's basically hashing it together. And then when you ask the Bloom filter, have you seen this element ever? Like, do you contain this element? It will answer with approximate Boolean. So, yeah, I have seen this element, and I'm rather certain I have. So the problem is if you have a too small Bloom filter, so it has this space where it's putting these basically have seen markers, right? So if you have a too small Bloom filter and slap millions of things on it, it can give you false negatives, but it will not give you false positives. Did I get that right? Yes. So this is why you're always looking at the how sure am I about this value? And if it's not sure at all, you probably just need to increase your Bloom filter size, which is configured here at the top width. So this is very useful in that kind of job. Again, a shop. You're grouped by the shop ID, so that's the same thing we did before. And then what I want to answer is, did this shop, did each of the shops sell Wurst, sell beer? And I need a yes/no answer. But I don't want to send around the entire history of what the shop was selling. So what I do is I construct this approximate structure, and then I can send it over the network to the map. And the map only asks this very small data structure, and that's usually enough. Okay. Yeah. a question one could ask here, yeah, why not just a set? Well, obviously the answer is it was out of memory, because we're talking about really, really big data sets. And as you noticed, there's this isTrue method, and this is just taking some default. I think it's above 90% certainty when we think it's true. You can configure that. Okay. So, joins. Joins are really funny in Hadoop because it's not made for it at all, right? It's this batch processing thing, and while you can implement the joins, it's not a very native thing for it. And what we end up doing in these implementations is basically reinvent the last 20 years of SQL databases, but anew. So one thing databases usually do when you have some data set, they estimate which data set do we move, basically. Or which data set do we load into memory and total, that kind of operations. So this is why we have the different versions of a join operator here. Because we're operating in a distributed setting, and we have to basically move this one pipe of data to this other pipe of data. By move, I mean send over the network. We probably want to send whoever is smaller. And we can't really easily check who is smaller without doing a full iteration. That's how Hadoop is constructed. So some programmer input is needed here. So in the first case, that join with larger means the left-hand side pipe is smaller. So we will be moving it to the bigger pipe. And the join with tiny is a very specific case where we do, again, map side stuff. So we do love map side stuff because it's very, very efficient because we don't send the data at all. But the join with tiny means the right-hand thing is very, very small, as in fits in memory. So what we do instead is we take the other pipe and send the entire collection to the mappers. The entire collection goes to the mappers before the reduce phase even starts. Each mapper loads the small collection into memory, does the joining, and then sends stuff to the reducers. This again can reduce the number of data we send around. Right? If nothing joins, we send nothing. Yes. And yeah, usually you will be forced to do the big moving thing anyway, but if you're able to join with tiny, is a big time saver. And there's plenty of examples where it actually works very well. For example, you want to check, you have some data stream about people, and you want to merge it with some stream that is sex-oriented in terms of, is it a woman, is it a man? That's really tiny. It's 2 fields, right? We can send that small data set and do the merge on it. Okay, let's look at an example. So I have some people, and I have some cars. And as you can see, I will be doing the join by left-hand side ID, right-hand side owner ID, to find out who is this car belonging to. And yeah, here I'm doing one weird thing. Hadoop is full of weirdness. So what we do here is function implicits, which provides me the ability to write this guy as you would expect. Like, this looks nice. But with the change from the previous examples, that I'm using here multiple fields on the read side, right? Because I want to construct a message that says, hello name, your car, blah, blah, blah. So I need both fields. And if you wouldn't include these implicits, you have to fall back to manual tuple extraction. It's a small API failure, but thank goodness this guy solves it. The reason it isn't provided right away is it doesn't play well with some of the normal collections operations. It does weird things, and you would sometimes not be able to compile a normal map on a normal collection because of implicit conflicts. Okay, so the join with larger is rather simple. You just say left-hand side ID, right-hand side ID, and the check is only equality, right? And it's Java equality in terms of the equals method. Yep. So the example would produce this kind of data. Okay. Like I said, the map site join is implemented with the join with tiny. And there's some intuition here about when to use it. So you can actually also use it not only if it fits into memory, but if the number if the sizes of the elements are very skewed towards the left-hand pipe. Because it will spill to disk if it doesn't fit into memory. So this guy will not magically out of memory if you just send over a very big thing. It will be just inefficient, but it won't blow up your job. And then there's the worst case scenario of trying to do a join of one person, let's say tweets. So President Obama tweets something interesting, and everybody is retweeting it, like the entire US. So we have a very skewed join where we have one tweet and a few million tweets on the other hand. How the usual joining algorithms work here is they distribute the pipe to a few nodes, and everybody does a part of the join. Yeah, we can't distribute it if the left-hand side is one element. So what this would end up being, if we don't use skew joins, like these methods, it would be stuck on one node, and this one node would have to deal with everyone. So this method of skew joins is basically iterating over the pipes, but with a very small sampling rate. So that's the setup here. So we go like every 1,000th element, and if we detect that it's very skew, like we see this ID 20 is like all the time everywhere. Of course, this can get things wrong. Don't get me wrong. This is not a precise method, but it usually helps for these extreme cases anyway, because you would see that even in a very small sampling. And then we replicate that very, very often joined 2 guy to multiple nodes, and then we do the joining again. So it requires more setup, but here it's not too bad. We just do the same thing and provide this configuration. Stepwise, it's like I said. We sample the pipes, then we determine who we need to replicate, we do the replication, and then these are joined. Okay. Yeah, the big question of this entire talk is it's not very type safe, as in not the company. So what can we do about that? I mean, the big problem is these jobs take hours to compute. And if you make a small typo or the data set changed and you didn't notice, someone refactored things and you didn't notice and didn't change the type, you would get this guy. Like number format exception for Bob because it's not user ID now it's username because someone changed the CSV format. And the worst thing is you get this after a few hours of computation when it gets to that phase of the MapReduce job. So let's try to avoid that. Well, there is a quick fix. If anyone wants a very quick fix or you're just trying out different things, sometimes just adding a trap, so second line here, is useful enough. What this will do is each time we have an exception during some of the steps, we write the exception to this errors file. And then you know which element produced the error, and you can maybe filter out the data because you suddenly they divide by 0. Oh, so you're like, so I'll filter out the 0 elements, that kind of things. Because sadly, most of the data is a little wrong all the time. All the data sets you get from the real world are wrong in some way, at least a few elements in this big chunk of stuff. So yeah, that's the quick fix. But the proper fix is using the typed API, which looks like that. Nope, like that. So input the typed DSL, and then you need to provide the types up front, right? So in the field DSL, for each map operation, you were choosing different fields and assigning the type var ad hoc. But here we have to give the types in advance, and then what we get into in this pipe is a more Scala collections-like experience. So you get a kind of iterable of this tuple thing. This doesn't play well if the tuple is very big, of course. For one thing, you lose readability, etc. But there's ways around that, and we'll see that in a second. So you have to give a type for every field you're reading in. And even here, let's still remember that we have these different phases. And this is basically the planning step, the assembly step, this code that we have here. So what if we make a mistake here? That the tuple arity on the left-hand side doesn't match the right-hand side. Sadly, yeah, you could do that with macros, but with just bounce checking it's hard to detect this here without duplicating the method all over the place 20 times. So what this will do is it will blow up during planning phase. So planning phase is the first 20 seconds of when you submit the job. So we don't blow up 5 hours into the job, but right ahead. It's some gain, and it saves you from small typo kind of errors. Okay. So what usually would happen is there will be a few data sets that you use all the time in your jobs. So instead of doing this source that I can have a typo in each job, you would have a trait where you define these once and then have a named method, for example, that gives you a new source all the time. For one thing, it's more readable. For the second thing, you can have builders, because if you have daily or monthly snapshots of your data, well, in the Hadoop world that does happen, like monthly or yearly aggregate thingy, then you can easily just do it here, or if you have a per country file, etc., etc., etc. And of course, just by the way, it's not limited to files. Scalding can operate on random, arbitrary, whatever you want to implement source of data. So I was using HBase tabs, worked pretty good, and people use it also with Cassandra, etc. We are not bound into only Hadoop stuff. It's a very Hadoop agnostic abstraction. Okay. And yeah, here we are not bound to field names, as in the fields API. We were saying the symbol name like 20 times in the job. So what happens if someone replaces the name with a first name, right? So here we are not bound to that, but we have the not niceness of using tuples for everything. That's not really readable, especially since the big data jobs usually operate on primitives. So it's this int and the other int is that the same int. So what I would usually do is have this pipe do the deserialization for you. And then you work on person, book, movie, shop, whatever. And this is starting to look nice, I guess. Maybe to me. Okay. And of course you can do typed joins. That's a relatively new feature. And I never got to using them, but I figured it's a very, very nice thing, so I'd love to show them. So we basically have a small DSL for doing the joins. Pretty much similar to the Mongo DSLs that you may see in Scala. And the good thing about it is, since you do the planning, you can optimize the jobs this way that the mappers do the read from the free sources, and they can do it in one MapReduce step. Because the naive way of a free-may merge in that kind of setup would be merge here and then merge again. So you have two MapReduce jobs. That's costing some time and again transferring data. So thanks to the planning phase, we are able to optimize some things here. Yeah, but how do you know the optimizer did what you think it did? Because I can just claim, oh yeah, this will be optimized. But sometimes it isn't because some weird edge case somewhere. So you can run the app with tool graph, which will produce a dot file. So dot is this language for describing graphs. I think it's visible enough. Basically, numbers and edges with labels. That's it. And here on the digraph on the top, you see the label is the operation every of these blobs is. So whenever you see a group by, you know, oh, it's doing the reduce step. And whenever you see every, that's the third element here. So every is the cascading vocabulary for map. Because for everything, we apply some function. So that's a very simple example of a word count. And yeah, you do have to do a little bit of thinking and look at it to see where the map is ending and where the reduce is starting. So by magic, you won't know that. You have to notice that, oh yeah, this element is a group by, and I know a group by will force a reduce. Yeah, so a real life example would be this guy, which does similarity checking and then output to two different databases. So what you can see here is at some points it does this two jobs at the same time, right? So you also gain parallelism if the jobs are independent. But sometimes there is a group by a join from these two sources, so you do have to wait for that guy, of course. So this is a very powerful tool to debug your pipelines. The other powerful tool to debug your pipelines is, yeah, not debug them, but test them. And there's pretty good support for that. So you just do a job test, give it a class, provide the arguments, and do some mock sources and sinks. And inside the sink, so the out parameter here, you can do all kinds of assertions. So I'm just using Scala test here. Okay. Now, one little difference here on the last two lines is, so Cascading provides a local mode, which is not touching Hadoop at all, which is faster, that's nice. But sometimes it can yield, yeah, not the same behavior. So when you call run, that's using the in-memory re-implementation. And if you call run Hadoop, that's actually spinning up Hadoop, but still locally, right? You don't need a cluster for that. Okay. I was hoping that's not a click-by-click slide, but that's a small summary of what it gives you. And two things I didn't manage to talk about today, but there is a very nice matrix API, because if you have a list of tuple, that's basically a matrix, right? And there's plenty of algorithms which depend on matrices. So there's a nice API for that, which also optimizes many of the matrix operations. And if you want to get started, there is a very nice activator template which includes some of the hello worlds and a few known examples like the inverse index, etc. Just give it a try, use the activator and a bunch of links, and I'm open for questions if you have some. Do we have questions? I do give out stickers for questions, like this one. 5, 4, 3, 2. It's not combiners. The map operation is prepared by Cascading to do it in there. And when I say replicate, the replicate thing is using the Hadoop cache. Yes, please. Yes, it is another DSL. So you can't just translate, I take my Scalding job and slap it onto something, but it is a different DSL, but it provides most of the same capabilities. The upside is you can run it on Storm or on Hadoop. So the use case is you have your yearly report thing, and it's actually the same as I want to see the last 5 minutes of traffic. And the operations are the same, but you need it in both cases. So that's the use case. Or use Spark. Problem solved. Hugo, you had a question. Well, mhm. Yeah, I wouldn't say better. That was a slip of tongue. I wouldn't say better. And Spark, actually, it's still batching. It's not a streaming thing, even if it does like to look like it. So they have this module, Spark Streaming, so it's even called streaming, but it's not really. So the difference is they have this endpoint, they take the traffic, for example, you're collecting traffic data, that endpoint gets hit with data, but the processing is still a very small batch, like last 5 minutes of data. And then they fire up a very small batch. Although I haven't used Spark too much, there's a guy from Databricks here, so if you have questions, he's probably a better guy to ask. Yes, very in the back. I forgot your name, sorry. Yes, this guy. I forgot your name, sorry. Michael. Hey, Michael. Okay, so thank you very much. If you have any more questions, come and grab me. And there's another talk from me and the Akka team about Akka persistence. So, see you later, maybe.